Hi everyone, welcome back. Today we will be looking at the Southern Province. And the Southern Province is an area of geology which mostly contains rocks that are Paleoproterozoic in age. And this particular little area of geology, it's located on the northern shore of Lake Huron, is one of the most interesting parts of the Georgian Bay. And that's because it's actually the best record of what the world was like during the Paleoproterozoic in the entire world. It just has absolutely spectacular geology. So the main two topics that we'll be looking at are what the rocks can tell us about Paleoproterozoic plate tectonics, and then we'll look at the sedimentary record and talk about how things like climate worked during the Paleoproterozoic. Before I begin in earnest, this is a quick overview of what's going on in the world at this time and what had happened in terms of Earth's evolution prior to the rocks that we'll be looking at today. And the Paleoproterozoic spans from around 2,500 million years ago until 1,700 million years ago. And another way you could say that is 2.5 billion years to 1.7 billion years. This is part of the sort of overarching time period called the Precambrian. And we call it the Precambrian because it happens before the Cambrian. And of course, you may have heard of the Cambrian explosion. The Cambrian explosion is a particular event in Earth's history that happens right at around 540 million years ago, when life became complex all of a sudden. So prior to the Phanerozoic means visible life, there really wasn't very much sort of large multicellular life around with hard body parts and that sort of thing, which means that there aren't very many fossils. So we're in the Precambrian, and we're in the latter part of the Precambrian called the Proterozoic, but we're in the earlier part of the Proterozoic called the Paleoproterozoic. So the part of the Proterozoic that happened the furthest ago. We have three sort of sections within the Precambrian. The first is the Hadean. That's when the Earth was sort of still cooling from a molten state. We might have had the first sort of crust start to form. By the time we get into the Archean, we had not just crust, but continental crust. These little pieces or fragments of continental crust started to move around the globe, which meant that there were plate tectonics, or plate tectonic activity was actually happening. And as a result of these little fragments of continent moving around the globe, we had supercontinents, which started to form. So the first supercontinents were in the Archean. And on top of this, we had the evolution of photosynthetic life. And this life was very primitive, really just green algae and that sort of thing. By the time we get into the Paleoproterozoic, all of this photosynthesizing green algae had started to pump oxygen into the oceans and then later into the atmosphere. Therefore, the Paleoproterozoic has a really important event in it, which is the Great Oxygenation Event. And that just sort of refers to the gradual buildup of oxygen in Earth's atmosphere. And by the time we get into the Paleoproterozoic, we have the second supercontinent at least, which is known to have existed, forming, and later breaking up. So let's start by examining the plate tectonics of the Proterozoic and how those plate tectonic events influenced the development of the Southern Province. We're going to start by talking a little bit about the Superior Craton. A craton is basically just a solid piece of continental crust that has behaved coherently for a really long period of time in Earth's history. The Superior Craton itself came together through a series of orogenies and collisions, plate collisions, prior to about 2.7 billion years ago. So this was during the Archean. And it itself is comprised of a number of ribbons of different rock types. And each one of those ribbons probably represents a microcontinent. So in this image, for example, we have pink plutonic rocks. Those are those igneous rocks that cool in magma chambers deep underground. In the green, we have volcanic plutonic rocks. So a mixture of igneous rocks that erupted on the surface, and usually they're magma chambers that fed them underneath. Most of these green belts were probably created above ancient subduction zones. And in many cases, those green ribbons are separated by yellow ribbons of metasedimentary rock. And these metasedimentary belts are probably created when we have compression of little wedges of sediment between colliding volcanic or magmatic arcs, again, during orogenies. There's also a little bit of gneiss. The Superior Craton was most likely part of at least one, if not more, Archean supercontinents. And I should emphasize that it's often very difficult to define Archean supercontinents because it's really hard to trace paleogeography back 2.5 or more billion years. It seems likely, though, that the Superior Craton was part of a supercontinent with several other blocks of similar age, and sometimes we call that supercontinent Kenorland. Sometimes we call it or Arctica, depending on which blocks we think are involved. Here we see some modern geology, really, and the modern distribution of the provinces. We have the Superior Province, which goes throughout most of Quebec and Ontario. And there are also several other cratons now incorporated into the Canadian Shield. These are things like the Hearn Craton or the Ray Craton, as well as several others. And they are similar in age to the Superior Province, but probably weren't located in the position in which they are right now relative to the Superior Province. So they may have been sort of floating blocks elsewhere in Kenorland. Throughout the evolution of the Southern Province, these continental blocks will come into contact with each other in a series of different orogenic events, like, for example, the Trans-Hudson origin or the Pinokian origin, which actually affects the Southern Province itself. On the right-hand side, we just sort of see a map of the Southern Province in red relative to the Superior Province in orange, just in Ontario. And we can see that it includes rocks that lie to the north of Lake Huron, up to the Cobalt region, and also to the north and also to the west of Lake Superior. So in this cartoon, we see Kenorland, and it starts to break up along a triple junction. This is a fairly typical thing that happens during the breakup of a supercontinent, as continental crust rides over something like a mantle plume. We get usually a series of triple junctions that connect up with each other in order to initiate the breakup of that continental landmass. That joining up of triple junctions into some sort of linear feature is called a rift. And it's along that rift that blocks of continental crust start to diverge from each other. So the Superior Province starts to diverge away from some other craton, and it's not completely clear at this point what that other craton was exactly. Over time, those two continental blocks drift apart from each other, and this is called the drift phase. And what used to be a rifted margin of the Superior Province becomes what's called a passive margin. The rocks of the Huronian supergroup, which are the oldest rocks of the Southern Province and are mostly sedimentary, represent the fill of detritus, or sediment, into this new ocean basin that is forming. This is just another image to kind of try to illustrate some aspects of that process, but it's very generic. What we essentially have during the rifting of Kenorland is this rift-to-drift transition. So today, for example, we have parts of the world that we can look at to compare to. So, for example, the East African Rift is a big rift valley, and it's a place where magma is seeping up through the crust, and the crust is getting thinned as those two now individual plates start to move away from each other at a new plate tectonic boundary. Magma seeps up through those fissures or cracks and erupts on the surface. What we see, for example, in the Huronian Basin are just thousands and thousands of these dike features, and they're usually basalt dikes, or in this case diabase, which is really just a fancy name for a basalt that has cooled underground. Over time, more and more eruption of magma forces those continental blocks apart, and new oceanic crust is generated. This would be the creation of what's called a new passive margin. And a passive margin is the margin of a continent, but not necessarily a plate. So a passive margin is where there's a transition from continental crust to oceanic crust without the actual existence of a plate boundary. The plate boundary is located along something like a mid-ocean ridge. Later on, at some point, subduction is initiated at what was formerly a passive margin. And remember that subduction destroys oceanic crust. So over time, we have destruction of oceanic crust, and that eventually brings two continental masses back together with each other. And that creates two things. First, it creates new volcanic arcs and magmatic arcs, where we have subduction causing volcanism. And we have orogenies that start to happen as we get collision between those continental blocks. So if you remember way back when we were talking about fundamentals of geology earlier in the course, this is what's called the Wilson cycle, and it explains the opening and closing of ocean basins. The Southern Province records really an entire Wilson cycle from the opening of the Huronian Ocean to the closure of the Huronian Ocean and the creation of a new supercontinent. So we've gone from Kenorland to Nuna. Here we have the completion of this process in cartoon form and the making of Nuna. So as a new terrain, which is, the new terrain is most likely related to volcanic activity above subduction zones, and possibly the incoming of new pieces of continental crust, we actually get warping, folding, and thrusting of the sediments that were once laid down in the rift basin and on the passive margin of the Superior Province. And there are a number of orogenies that together make up the supercontinent of Nuna. This area highlighted in yellow is just sort of the Laurentian part of Nuna. But by the time we actually get to the creation of Nuna, which is around 1.8 billion years ago, We have rocks of the Superior Province have joined with those of the Slave and Ray and Hearn provinces in what's called the Trans-Hudson origin. That was around 2 billion years ago. And then more importantly for the Southern Province, we have collision of various magmatic terrains with the southern margin of the Superior Province, and that folds all of that sediment. That's called the Penokian orogeny. In this image, we can actually see the results of the folding and thrusting of those sedimentary rocks of the Southern Province. So, for example, we see this kind of white line that curves around and comes back into the North Channel. And that is essentially a giant fold structure. And it's picked out on satellite because it's made out of a particular resistant rock type that sticks up a little bit, even now, even after 2 billion years of erosion. It's almost a little bit easier to see on this figure. This is more like a terrain map. And what's quite interesting on this figure is we can see how the different rock types of these different geologic provinces really influence the terrain. So for example, the Superior Province is sort of knobbly, but generally low relief, kind of flat. Well, the Southern Province, which are deformed sedimentary rocks, we can see all sorts of these little ridges and streaks around Elliott Lake, for example, and we see some streaks up towards Espanola. These are really just sedimentary units that are standing up on their edges. This fold here are the rocks of the La Cloche Range, which is quite a well-known mountain belt even today. To the south, we have the rocks of the Paleozoic platform. These are much, much younger. They're only around 450 million years old or so. And these have never really been directly affected by an orogeny, which means that they're sedimentary rocks that are still fairly flat. As a result, they look essentially flat. You'll have a little bit of a chance to explore this region in the virtual field trip after this talk. And in that trip, we actually go through this area and look at the details of some of the rocks that are preserved there. This is an image of the La Cloche Range. We can see this sort of chain of low mounded white mountains. And of course, they're low because they've been subjected to erosion for the last 2 billion years. Another important part of the Southern Province actually mostly outcrops to the west of Lake Superior, and this is called the Animikie supergroup. The Animikie supergroup is in parts equivalent to the Huronian supergroup, so includes sediments that were deposited in that rifted margin of Superia, but it also includes sediments that were deposited during the Penokian orogeny. So the younger part of the Animikie supergroup is what's called a foreland basin. And a foreland basin is effectively usually quite a wide basin that develops during mountain building. So effectively what happens is mountains are heavy and they tend to weigh down on the crust a little bit. So if you have a great big weight like a mountain belt collide in with the margin of a continent, it actually presses down on that just a little bit, and it creates a basin into which water can flow and into which sediments can collect, and particularly those sediments that are eroded off of the new mountain range. A good example today is in South Iran, where you have the Zagros Mountains, and they are pushing down on the crust in order to create this waterway called the Persian Gulf. The Anamiki supergroup is historically quite important because there are big iron deposits within it, and also it's sort of a historical side note, but at one point it was thought to have the oldest fossils in the world. So this was sort of in the 1950s, and what was discovered were these kind of bulbous shapes within the layered rocks, the layered sedimentary rocks. And these bulbous shapes are what's called a stromatolite, and they are created when you have layers of algae on the seafloor, and they're a little bit sticky, so they tend to trap sediment, and they end up making these kind of bulbous, wrinkly shapes. So this was discovered in the 1950s, and at that time it was really some of the oldest life known on the globe. Now nowadays we have seen some fossilized microbes that are older than this, but still it's kind of an interesting fact about this part of the world. Another really important event that affected the evolution and geology of the Southern Province is the 1.85 billion year old Sudbury Impact event. So this was a great big meteorite impact that created a great big crater. When you have something like a piece of, an asteroid impact the surface, that tends to create a lot of dust. It blows a lot of dust into the air. It can get spread all around the globe. And it also liberates a lot of metals from the ground. This is why Sudbury is called the Big Nickel. So here we see the general outline of the Sudbury Impact crater. And you'll notice that the crater has been squished into something more like an oval. And that's really a result of the various orogenies that have affected the area since this time. So it would have been roughly circular when it first formed. So by about 1.7 billion years ago, Nuna had basically finished coming together, but the margins of Nuna, along which the Southern Province was located, effectively became what's called an Andean-style subduction zone. So there was a great big ocean surrounding the supercontinent of Nuna, and parts of that ocean were being subducted underneath the supercontinent. Just like today we have an example here, we have South America and the Andes Mountains, and the subduction of the Nazca Plate underneath the Andes. And that creates a lot of things like plutonism and volcanism. This is going to be really important later on because it's sort of a herald or a precursor to the upcoming Grenville orogeny. Because eventually what happens is the destruction of this oceanic crust off the coast of Nuna brings a whole bunch of new island arcs into contact with the edge of Laurentia. And that's going to be our next major orogenic event next week when we talk about the Grenville orogeny. So let's just quickly summarize the various parts of the Southern Province. To start with, we've got the Superior Province in pink, sitting up here, and the Southern Province is all of these different colored terrains or colored areas located on the southern margin of the Superior Province. The oldest rocks are those of the Huronian supergroup, which were deposited within the rifted margin of Superia. Following that, we have a number of large dike swarms which reflect the breaking up of the Superior Province with some other craton that it would have been attached to. Between about 2.2 and 1.8 billion years ago, we had the rocks of the Anamiki supergroup, mostly getting formed in the Anamiki Basin to the west of Lake Superior. So this is this yellow swath. Around 1.85 billion years ago, we have the Sudbury meteorite impact crater forming. And that's right, just coincidentally, on the edge of the Superior and Southern provinces. By around 1.8 billion years, various magmatic arcs, shown in the pink here, had come into collision with the edge of the Southern province, and that resulted in a great big fold and thrust belt shown in the dashed lines on this image, known as the Pinokian orogeny. And the Pinokian orogeny lifted up a bunch of mountains, and it also caused more sediment to be shed into the Anamiki Basin. By about 1.7 billion years ago, Nuna had basically formed, and there was active subduction happening along its edge. And this resulted in things like the Killarney magmatic suite, which is this pink little sliver right on the edge of the southern province. By about 1.3 to 1.1 billion years ago, we then get into the next major phase of the evolution of this part of the world, which is actually the Grenville orogeny. And the Grenville orogeny we'll talk mostly about next week, but it's associated with mountain building in the Grenville province, but also rifting in the southern province. So we haven't really talked about this yet, but there's this purple area kind of around Lake Superior, so it's probably the reason Lake Superior exists, called the Mid-Continent Rift. And the Mid-Continent Rift is basically a new rift basin that forms about 1 billion years ago when Nuna tries to break up amongst the sort of chaos of the Grenville orogeny. So that was a lot of information, and let's take a break there. When we come back, we'll look more at the details of what the sedimentary fill is of the Huronian Basin and what that can tell us about the climate during the Paleoproterozoic.